In this lesson, we are going to find force on a dielectric slab at constant V. When books do this derivation or when teachers do this derivation, they make the maths very complicated. And I will make the maths very simple because physics is simple. So we have a battery which can give an EMF of V. This battery is connected to a capacitor. L is the length of the plates and B is the breadth of the plates. So this is a plate, length is L, B is the breadth. And this is the capacitor. A dielectric of same dimensions, length L, breadth B, and same thickness D, the distance between the plates, is now partially inserted into the capacitor. So because this capacitor is connected to a battery, this plate will get plus charge, this plate will get minus charge, so plus Q here, minus Q here. Because of induction, some charge will get induced here, minus charge on the dielectric and a plus charge here on the dielectric. Okay, this is because of induction. Now because of this charges will experience a force this way, these charges will experience a force this way, and therefore the dielectric will experience a force inwards. We want to calculate that force. Now, when this capacitor is partially filled with dielectric, this is the dielectric, say X length of the capacitor is filled with dielectric, and L minus X length of the capacitor is filled with air, then we can take these two capacitors to be in parallel because same V is acting across both of them. So X length of the dielectric is inside the capacitor, and therefore this is one capacitor, this is an air filled capacitor, the other one, and both these capacitors are in parallel. The equivalent capacitance therefore will be C1 plus C2. That will be equal to the capacitance of the air filled capacitor will be epsilon naught into the area, which will be L minus X, into the breadth divided by D, and C2 will be the capacitance of the capacitor filled with dielectric, that will be K epsilon naught. Now the area of this part of the plate is X into B divided by D. So this is the capacitance of this capacitor at this instant when X length of the capacitor is filled with dielectric. So therefore, here we can take epsilon naught B by D common, and inside brackets we get this L minus X plus Kx. So therefore we can say this to be L plus K minus 1 into X. This is the capacitance of the capacitor at this instant when X length is filled with dielectric. As this dielectric goes inside, capacitance will change, and that change in capacitance DC will be given by, we differentiate this, we get epsilon naught B by D, and this differentiation will be 0, so you'll get K minus 1 into dx. So as this dielectric goes more inside by dx, there is a change in capacitance DC given by this formula. Now the energy stored in the capacitor is given by half CV square. Here V is constant, capacitance is changing as the dielectric is going in. So potential energy will be half CV square. Therefore the change in potential energy du will be equal to half V square dc, or V square by 2 dc. This is the change in potential energy as the dielectric goes in by x. Now here the energy is supplied by the battery. So energy is supplied by battery, and that energy will be used for two purposes. One is to do work, to move slab, and second is to increase the potential energy, that is du. So this is energy conservation equation. Energy supplied by battery will be used for two purposes: work done to move the slab and increase the potential energy of the capacitor. Energy supplied by battery will be the extra charge that comes from the battery dq multiplied by the potential difference V. Charge into potential difference gives us energy, work done to move the slab. Work done to move the slab will be force into displacement. So force is F and dx is the displacement, and the change or the increase in potential energy rather is V square by 2 dc. Now this dq is the extra charge coming in. This is due to the extra capacitance. So this will be equal to V into dc. Q is CV. So here C changing by dc and V is remaining constant. So dq is V dc. And you multiply this by V equal to F dx plus V square by 2 dc. Now this is V square dc, this is V square by 2 dc. If you take it this side, okay, we'll get V square by 2 dc. So basically F dx is equal to V square by 2 dc. And dc we know. dc is epsilon naught B by d k minus 1 dx. And if you look at these two equations, this dx and dx will cancel, okay, and therefore this V square by 2 is there, okay. So F becomes V square by 2 epsilon naught B by d k minus 1, and this is what is the force, and this force is constant. It does not depend on x, and with this force the dielectric will be pulled inside. So F equal to constant, and it is not a function of x. So this derivation is as simple as that, nothing complicated. If you see books, you'll get scared. Okay, so here battery was connected, V was constant, and this was a parallel plate capacitor, and dielectric was inserted up to a distance x. So we had two capacitors in parallel, one filled with air, other filled with dielectric, and these two capacitors were in parallel. C became C1 plus C2, and then we found DC, and then potential energy is half CV square. Here V is constant, C is the variable, so du became V square by 2 dc. And then we applied just energy conservation. Energy supplied by battery will be used for two purposes: to do work to move the slab inwards and to increase the potential energy. Work done to move the slab inwards is F dx. The change or the increase in potential energy is V square by 2 dc, and the energy supplied by battery is dq into V. And dq is what? V dc, because V is constant, C is varying.